Assalamualaikum everyone, I hope you all are doing well and taking good care of yourselves. This is your instructor Ali Faruqi and we're watching Science with Ali. So in today's video we're going to be diving into the fundamental building blocks of chemistry called the three states of matter. Now we will be using the kinetic particle theory to understand exactly how solids, liquids and gases behave. Now think of this theory as a way to visualize matter by imagining every single particle as a small sphere, right? So let's get right into it. Now these are the objectives for our class today. You can check the syllabus. I have screenshotted this part of the syllabus that we'll be covering in this video today. Now these are the three bullet points that we need to cover: the distinguishing properties, the structures and the changes of state, which we'll get into at the end. So let's get right into it. Okay, so properties of matter. Now, have you ever wondered why you can easily pour water out of a glass, but you definitely can't pour your desk? It all comes down to their properties. Solids have a fixed shape and a fixed volume. They are totally locked in, meaning you can't compress them. Liquids are a bit more flexible. They keep their volume, but they can flow to perfectly match the shape of whatever container you pour them into. And gases, they are the ultimate rebels, you can say. They have no fixed shape or volume and will expand to fill up an entire room if you let them, which is exactly why gas is highly compressible, right? I have jotted them down right away. You can take a screenshot of this or note this down in your register. Okay, let's move forward. Particle arrangement. Now, let's zoom in on the actual particle arrangement. Now, in a solid, it's like a tightly packed crowd. The particles are held together by strong attractive forces in a very neat, regular lattice structure, right? The liquids are more like a crowded dance floor. The forces are weaker, so the particles are fairly compact. They are present in clusters, but they are arranged completely randomly. Now, moving on to gases, we can say that they are, if you remember COVID, there was something called social distancing, right? So gases are like social distancing at its finest. The force of attraction are incredibly weak, leaving the particles completely far apart and scattered at random, meaning that the spacing changes matters. Now moving on to particle motion. Because of these different arrangements, the particles move in totally different ways. In a solid, they can't really go anywhere. These solids vibrate in place, right? Imagine them constantly jostling shoulder to shoulder. Now, when you heat up a solid, the solid particles vibrate so much that the solid actually changes shape. If you notice something, if you, for example, don't do this at home, but I experimented one time in which I took a spoon, I heated it over a stove, and I took the measurement before I heated the spoon, and I took it after I heated the spoon. There was approximately 1.5 to 0.6 centimeter difference between the two measurements, meaning that the solid expanded because of the vibration that took place. Now moving on to liquids, they have a bit more freedom to smoothly slide past one another. Now liquids can slide, right? Now we can say that the liquids are in clusters and they can slide over each other and they can go about their business. Now, moving on to gases is where it gets chaotic. We say gases are in constant random motion, but here is a pro tip. Gas particles actually travel in completely straight lines. It only looks random because they are constantly zipping around and ricocheting off the walls of their container or crashing into each other, right? So the movement of all the states of matter differs between states depending on how closely they are held together and how much freedom they have to move. Now moving on to the big parts, which are the heating and the cooling parts of states of matter. So how do we force these particles to change their state, right? We add heat. Heating gives the particles more kinetic energy. When you heat a solid, the particles vibrate faster and faster until they overcome those strong forces and they break. Now, when we break, we hit the melting point, which is exactly what happened here. The ice has melted and water has come out at the bottom of it. Keep heating and the particles move even faster. The liquid particles will break and then the gas particles will evolve. Now, at the boiling point, the particles gain enough energy to break attractive forces throughout the liquid, right? By the way, remember that boiling happens throughout the whole liquid, but evaporation happens in certain parts of the liquid, right? This only happens right at the surface where the absolute fastest moving particles manage to escape even below the boiling point. For example, if you look at um, if you look at the road, for example, and spill some water over a road, and the sun is right on top of that puddle, right? So on when you notice that puddle after an hour, it will look like the puddle has shrunk. Why has it shrunk? The sun, it has not reached, the water has not reached the boiling point because of the sun. It is because the when the sun is constantly shining its rays on the water, obviously the liquid will gain kinetic energy, and when it gains enough kinetic energy, the top surface of the liquid, the particles on the top surface will spool off into the air as gas particles, right? That only happens right at the surface where the absolute fastest moving particles manage to escape even below the boiling point, right? So we will now move on to cooling. Now the exact reverse happens when we cool things down. By removing heat, we are stealing the particles' kinetic energy. Now gas particles slow down so much that attractive forces grab hold of them, condensing them back into a liquid and then further into a solid. Now cool that liquid further, you will get the solid, right? A quick disclaimer before we finish is that this particle model is amazing for visualizing these changes, but it's not perfect. In the real world, these aren't just completely simple spheres, they are complex atoms, ions, and molecules. So, to wrap this all up, with further cooling, the liquid particles lose more energy and slow down. They become locked in fixed regular positions, forming a solid. This is called the freezing point. Now, kinetic theory explains how energy changes cause all phase changes. I think we have covered this starting in the lecture. So, right, so these are the next class objectives. So this wraps up our states of matter part 1. In the next video, we'll take a look at the heating, cooling curves, and diffusion. As always, if you have any questions, you can drop them in the comment section down below. And I hope you enjoyed this video, and I will see you in the next class.